Hello, this is Mr. Stansbury. I'm going to take you through the notes on natural base exponential functions. At the end of this, you should be able to say, I can graph transformations of f of x equals e to the x. All right, so e is a value used to calculate continuous growth rates for things such as growth of bacteria, radioactive decay, and actually your smartphone uses it too for processing images. Okay, so E is an actual constant, and it's approximately 2.7183, and it's called Euler's number because Euler is the one that came up with that. Okay, so here's what we're going to do. We're going to graph the function and its parent function, f of x equals e to the x, that's the parent function, and then we're going to state the domain and range. So similar to what we just did, but now we're doing it with this e here as instead. Okay, so first thing we want to do is we are going to do f of x equals e to the x. Now let's we can certainly do this by hand, that's totally fine, but we've got our calculator that should help us out on this, so let's just do that. So we're going to do table, clear out whatever's already in there, and we want to just do e to the x. So we need to find the e to the x, and you can see the natural log, ln, which we haven't gotten to yet. That's coming up here in a minute, actually in a couple sections, but we've got e to the x. That's what we want. So we want to do second, and then e to the x. Now it doesn't actually give us an x there, so we've got to put the x there, which is this variable button here. Okay? So we get y equals e to the x, and that's all we want. This is going to be our parent function, right? So start at 0. Let's maybe, we can just leave it at start at 0. The steps go up by 1. That's good. And then off we go. So then we just keep pushing enter until it gets to OK. And then it's going to give us some numbers here. I'm actually going to go back up 1 to get to -1, just so we kind of get a little bit more info on that. So points that we have are at -1, and we'll call that 0.4. So our parent function, let's do the parent function in red this time. So at -1, we're at 0.4 about. Okay, so we can actually do that on both of these because we have to do it on each of these. At 0, we're at 1. So at 0, we're at, oh wait, that was supposed to be 0.4. Neither of those are a 0.4. Let's try that again. -1.4. That looks a little better. Sorry about that. And then at 0, we were at 1. 0 is at 1. And then at 1, we're at 2.7, which makes sense because there's Euler's number. 1, we're at 2.7-ish, so about right there. Okay, and then we could keep getting more and more numbers, but we can kind of see what's going on here. There's an asymptote, because really this is +0, right? So there's an asymptote at 0 on these. So then we know that our graph is going to look something like that-ish on both of these. Okay. You get the idea. So there's the red is the parent function, f of x equals e to the x for the red. Okay, so then now what we can do is let's do these transformed functions here in blue. So really all we're doing is we're taking all of these y values and multiplying by -2. Okay, so we could do that by hand, or again, we can just go into table. That's what I meant. And we want to do -2 e to the x. So let's do this. -2 second ln is the e to the x, e to the, and we got to actually put the x in there. And then we push enter. And then start at -1. That will actually be good for us because that's where we started the other ones at. Push OK. -1 is at -0.7. So -1 is at -0.7. Oops, just on this one. I was going to do it on the other one too. That wouldn't make sense. 0 is at -2. And 1 is at -5.4. 1 is at -5.4. So roughly right about there. Okay? There is no number out there, so that means the asymptote out here is going to be at 0. So this one's also going to have, it's going to have the same asymptote. Okay? So then we can tell that this graph looks like this roughly. Okay? So there's the original and there's the parent graph. Okay? All right, let's take a look at the second one, but maybe before we do that, let's take a quick little comedy break.
I'm old myself, I get it, man. I can prove it to you. This is how I know I'm old, okay? This is how you know when you're old. If you're on the cusp and you don't know if you're old or not, this is how you know. If you fall and no one laughs, you are old. That's how I know I'm old. It happened to me. I failed. Everybody, oh, sir, you okay, man? Get off me. I'm an athlete. Move. I played college ball. Get off me.
All right. Let's take a look at this second one over here. All right. Oops, sorry. So we can, we could plug this into, we could go through and make a little T-chart and do all that stuff, or we can simply just plug it into our scientific calculator, which will give us all the stuff we need. So data, we want e to the, let's do this. Let's clear all the rest of that stuff out first. So e to the, and we've got x plus 2. So we got x plus 2 all in the power, and then we got to go over, and then we got to subtract 3. Okay? And then now we do enter. Start at -1. That's probably pretty good. Step by 1. And then it will give us our data. So at -1, we're at -0.3, we'll call it. So at -1, we're at -0.3. That's a little bit too low. There we go. At -1, we're at -0.3. At 0, we're at 4.4. Okay, 1, 2, 3, 4.4. So we're about right there. Okay, and then at 1, we're at 17. So that's like way up. I'm going to go with about right there. So that's not really a helpful one to graph. So let's do this. Let's go back to -2. So at -2, we're at -2. This gives us a little bit better idea. I'm going to go back even another one to see what we get. And then we're at -2. At -3, we're at -2.63. So that looks pretty good because we know we have an asymptote at -3. So we draw a little asymptote here. At -3. And so now we know our graph's going to look something like... Oops, got a little wiggly there at the end, but something roughly like that. Okay? Okay, that's all we have for natural base exponential functions. If you have any further questions, please feel free to ask. Thanks.